We will now continue with the practice of making presentations as we did yesterday. But here, before we begin, I want to make a few opening remarks. We have seen yesterday what appeals and what is useful to this whole audience when we make a presentation and what is not. First, let's focus on what is useful. What is useful is when you reflect your understanding of what you heard and saw in the video lecture that you are reviewing and presenting. What is not so useful is to go into minute details, because those minute details are anyway available to you later. We are not trying to teach the subject here in its entirety. We cannot possibly in such a short time. But we can teach how to teach. That is what we plan to do in 3 days. Or rather, we should say, we can evolve a methodology to learn how to teach. We can evolve a methodology to teach in these 3 days for E210.1x, and we'll similarly do the same for E210.2x between the 4th and 7th of December on the next weekend. Now, when you present today, you must keep in mind that you're going into relatively more advanced topics as compared to yesterday. Yesterday, we were looking largely at systems in the natural domain. Today, we will soon be looking at systems in the frequency domain. But before that, of course, we would complete a few points of discussion about systems in the signals and systems, the natural domain, particularly the operation of convolution and so on. Now, when people present the idea of convolution today, I would like you to emphasize how you can make this concept easier for the class to understand. For a beginner, the idea of convolution is not too easy at all. And therefore, when you present the whole discussion on how you're going to expose convolution, I would like to see how you as teachers would make this easier for a student to understand, more appealing to a student, more intuitively clear to a student. Further, I would also like you to participate actively in the critical discussion on the presentations. I must again emphasize that when we make a critical evaluation, or rather I wouldn't even call it an evaluation, when we make a critical appraisal of a presentation, we are actually doing a lot of good to the person who's presenting, because he or she is not losing any credit or not being belittled in the process at all. In fact, the person, by virtue of listening to your critical appraisal, is actually gaining in terms of pedagogy. It is better to be critically appraised today and to realize a few points and carry them into one's teaching and learning as one goes ahead from this workshop, rather than just make a presentation and be happy that people listened to it and went away. The third point which I wish to emphasize is that my teaching is already available to you in the form of the course. And that's why we are making this a dialogue. We are keen that I speak and you speak. It's not only I who am going to speak in this workshop, it's not only you who are going to speak in this workshop, it's both of us. And each of you is very important in this workshop. So don't undermine your own importance by being unparticipative. Make sure that you are actively involved in listening and critically reviewing the presentations. Today, when we come to the Fourier domain, the frequency domain, I would particularly like you to identify how you can bring in the geometrical interpretation into the Fourier domain representation, which has been emphasized in my lectures. I think you must have seen that. Well, so more as we go ahead, and I would not like to come between you and the people making a presentation today. So we'll continue with the stream of presentations, and now I'm very happy to invite again group 3. I don't know whether group 2 is group 2 ready now to make a presentation.
Yes, sir, we are ready.
All right, then let's have group 2 first. Let's have group 2.
Okay, sir. Okay, sir. Okay, so thank you, sir. Good morning, all. This is Meenakshi Atte, group number 2. We will be presenting our presentation on the topic of properties of discrete systems. The contents for this topic or the presentation, very first, we will discuss additivity and homogeneity. This will be presented by me,
Yes.
Dr. Meenakshi, that will be presented by Dr. Smita, and finally, stability by Dr. Prema ma'am. So let us start with the additivity and homogeneity. So the flow of the discussion would be, very first we will see the statement of the property, then we will go for mathematical equation or the representation, and finally the examples. So when we talk about the property, we know we all are aware of the statement, but as sir suggested, we should follow some methodology to explain the properties. So I'm writing the statement of the property first. A system is said to be additive if the output corresponding to the sum of any two inputs is the sum of the two outputs. So we all know this. So this is how we would like to present. So very first the statement, then the mathematical equation for that property. So input xn is given, that can be divided into x1 and x2. So these are the subsystems we would say, and the output corresponding to these two subsystems would be y1 and y2. So this is simple additivity property. And next is homogeneity property, where we can just remember this as a scaling property. So statement could be system is said to exhibit property of homogeneity. Input is scaled by some constant a, and then output will also be scaled by a. Then we have mathematical equation. So x of n we know. So everywhere we purposefully put the square bracket because as sir suggested, it's a sequence now. So we have to consider that. So we are we are thinking that purposefully we have to use this square bracket for the representation of the sequences. So input is xn. So it is now revised. It is a into xn. Then output will also be scaled. That's nothing but the homogeneity property. And this is a schematic representation. So whenever we stress on the visualization of the property statements, it's always good to remember the properties. So here x1 and x2, these are the two subsystems. So this x1 is producing the output y1t, x2 is producing the output y2t, and if we add them, we have this y1 of t plus y2 of t. So similarly here we have this representation. So it's like when we add these two, this is x1t plus x2t, and here we get y of t is equal to y1t plus y2t. So in a way, it's nothing but the left hand side representation and right hand side representation of a given property. So if they are same, we can say the law of additivity is been followed. Similarly, this is the representation, schematic representation for the homogeneity property. So we have this system. So x of t, it's applied to a system, it is producing some output y of t. If it is multiplied by this k, the output would be k into y of t. So we interchange these two blocks, and this is nothing but possible in case of linear systems. So x of t, it is multiplied by some constant k. So it will be k into x of t given, this is given to the system. So that will be pi dash of t. Right. So after the schematic representation, so let's see what is the purpose of these two property. So why do we need this additivity and homogeneity? Ultimately, they are going to result into the superposition theorem. So together these two properties are forming the superposition theorem. So we are representing with the mathematical equation t is some function a into x1 n plus b into x2 n is equal to a into t. That's the function has been separated. So that will be a into t of this x1 n plus b into t of x2 n. And this has been represented again with the block. So x1 n is producing y1 n, x2 n is producing y2 n. So together that will be given to this linear system producing this a into y1 n plus b into y2 n. So this is the example everybody knows. So I'm not going in the details of it, but just to have a clear idea about the linear systems. So this is the original equation y1 is equal to x1n plus x1 upon x into n minus 1. So when we apply some function to this equation, this is how we have divided into subsystems. So if we look at the LHS and RHS, so we come to know now this scalar a1 is appearing at the numerator and this scalar a2 is appearing at the but this A1 is appearing for the signal that is been given. So this signal is associated with this A1 and X2 is associated with A2. So this is how the system is not going. So we say this is not so once we are familiar with the statement, the mathematical equation, the schematic representation and examples, we can relate this concept with the help of some real-time applications like sound equalizer and volume fader. So sound equalizer, it's visually presenting the gain that is being given to a particular frequency. So these are the different frequencies available, and those will be either boosted. Right now they are at 0 dB, but those will be boosted or those will be attenuated. So that depends on the user or the application. So if you want to highlight or boost the low frequencies, or if you want to highlight the higher frequencies, so that depends on us. It's like we are giving some gain factors, so a into x1 n plus b into x2 n. So together all these instruments in a polyphonic signal, either they will be attenuated or they will be boosted. So that's again the typical example. So it may not be perfectly suitable to the linear systems, but this is just giving us an idea about the mathematical representation of the different signals available in the polyphonic signal. So here it's the visualization of the given system. So I would like to also give one example. Suppose we focus on this particular system. So here we consider this x1 x2, maybe it's a class or maybe a workshop of different people. So x1 and x2, I mean if these are the subsystems or sub elements, or if they are the participants, so if all are from same background, suppose in a workshop, the workshop is focused on science, and a few people are from art side, few people are from commerce side, and few people are from science side. So if it is particularly focused on science, then only science people will be enhanced, I mean they will gain more knowledge in that case. So that will be a homogeneous system if we consider it is totally of science people. If it is of say science plus arts plus commerce, that we can say it's the heterogeneous system. So the exact, I mean the expected output or outcome will not be given after this workshop. So we can just think of this homogeneity property and the additive property, which are nothing but very suitable for proving the linearity of a given system. So that was all about my part. So I will request uh, Manisha ma'am to explain the shift invariance property. Thank you, sir.
Thank
Thank
you.
you,
Thank you.
Meenakshi ma'am. Now I would like to go in for the second important property, that is shift invariance. We will be sticking to the flow of discussion throughout in a uniform way. So over here, shift invariance can be stated in different ways. A system is said to be time invariant if time delay or time advance of input signal leads to an identical time shift in the output, or the time invariant system responds identically no matter when the input signal is applied. In simple words, you can say that the characteristics of a system do not change with time. So these are the different ways how we can state the property. This is a this is a block diagram representation of the statement, wherein for simple understanding of the property, we show that in case if you delay the input and then apply it to the system, we get an output. In the second case, if you give the input directly to the system and then delay the output, in both the cases, the output should be the same. So that represents shift invariance property. Now we will explain this with the help of an example. So here we have taken a simple example wherein we have y of n is equal to x of n minus x of n minus 1. For simple understanding of solving the problem, we generally I prefer taking it as delayed input. So when you delay the input, that means x of n has now become x of n minus k. So the first output that has been obtained over here is x of n minus k minus x of n minus k minus 1. Now, in the second case, we simply delay the output. When I say we simply delay the output, it means that we replace n by n minus k throughout in the equation that has been given to us. So the expression that we get over here is x of n minus k minus x of n minus k minus 1, wherein in the place of n, I have written it as n minus k. So if you see y1 of n and y2 of n both come out to be the same, it means that shift in input has had no effect on the output. The input-output characteristics remains the same. So this is an example of a time invariant system. Now, we will support our statement with a counter example, wherein we have taken the example as y of n is equal to x of 2 minus n. Again, we are following the same procedure. First, we delay the input. That means instead of x of n, we take it as a function of x of n minus k. So the output that you get is x of 2 minus n minus k. And the second case, wherever we are putting n, we put it as n minus k. So you'll see that the output now that you have got is x of 2 minus into bracket n minus k, which comes out to be as x of 2 minus n plus k. And it clearly shows that my output has got affected due to the shift in time. And therefore, we say that this system is a time variant system. Now, we have supported our discussion with more examples over here because generally students find this property a little confusing. So to support it, we have taken an example of a moving average system. So if you see over here, it is of a similar, it's kind of a similar example that we had discussed as example number 1. So this is an example of a time invariant system. Now the second example, if you see, is actually a downsampler. So wherever it is x of 2n, you will see that now this system is no longer a time invariant system. This is an example of a time variant system. So you can support your explanation with a real-time example of a mixer. Whether it is a downsampler or an upsampler, a frequency mixer, you will always see that these are time variant systems. Now, I would like to give an analogy, a very simple analogy, which we just recently faced, like yesterday evening, due to some issues. Group number 2 could not give the presentation on the properties of discrete time systems. So there was a time shift. That time shift was, instead of afternoon, we shifted to the morning. But if you see, the characteristic of this system, group number 2 has not changed, but we made the same presentation on the properties of discrete time system. So even if there is a change in with respect to time, but there is no change in the outcome of this situation. So this is a simple analogy which I thought would be suitable over here. So now I would like to hand over it to Smita ma'am. Thank you.
Good morning to sir and good morning to all the participants. My topic is causality of discrete time systems. So the flow of discussion would be statement of the property followed by the mathematical equation and followed by the examples. The statement would be a system is said to be causal if the output at any time depends only on the current input and all the past inputs. So if you have a system and if there are any future inputs coming into the system, then the system will not be a causal system. It is rather a non-causal system. As sir pointed out in his lectures, causality refers to the cause-effect relationship being realized. So a mathematical representation of a causal system would be y of n is equal to a function of x of k, wherein k is less than or equal to n. So here x of k applies to the input and y of n is the present output. As long as the k value is within the range of n, or from minus infinity up to n, we can say that the system is a causal system. Here I would also like to mention that all causal systems are physically realizable systems. That is, whatever system that we design today, we design the system based on a knowledge of what can be the input and what could have been the past previous inputs. We take a feedback. So all feedback systems are physically realizable. At the same time, even all memoryless systems or all dynamic systems are also causal systems. So here, a simple example would be y of n is equal to x of n minus x of n minus 1, wherein we know that x of n is the present input and x of n minus 1 is the past input. So since the y of n, which is the present output, depends on the present and past inputs only, this system is said to be as a causal system. Whereas in the case of a non-causal system, y of n is equal to x of n minus x of n minus 1 plus x of n plus 2. Here, the only difference is x of n plus 2 is a future input. So because this system is taking into account a future input, this system is known to be as a non-causal system. So, like I said in the first slide, all physical systems are realizable. So, then what about the non-causal system? Here, I would like to discuss a few examples of we would like to I would like to talk about some real-time examples of non-causal systems and how it is applicable to us in the real-time application. For example, a sound processing. Consider a song stored in a sound file. Because the entire song is stored, we could process the sound by filtering it in such a way that has the current notes depending on the notes which are coming later in the song. So this is an example of post-processing, and this is a classical example of a non-causal system. In a similar manner, if you take up all image processing examples, pixels to the left of the current location can be considered as the past input, and pixels to the right of the current location, you could represent it as the future inputs. So therein, we are able to take about the image processing also as a non-causal system. And additional examples would be weather forecasting, how we are trying to forecast the weather, and how what about the population growth, how we expect the population growth to be. So these are some real-time examples of non-causal system. Thank you, and I would now like to request Dr. Prema ma'am to continue the session. Thank you.
Yes, thank you, Smita. Good morning to everyone. I'm Prema. I'm going to explain the property of stability for discrete time systems today. So here I'll be explaining the statement of property, the mathematical equations, and some examples for the stability. So the statement, the stability statement holds good for analog, continuous time and discrete time systems. The same statement. The statement is that the system is said to be stable if every bounded input to the system results in a bounded output. So here I want to emphasize the word bounded. The meaning of the word bounded is that the magnitude of the input at every discrete point, as it's a discrete system, so every discrete point is less than or equal to a bound. So here I have named the bound as K1. So here you can call it as any name. Only thing is that here we are assuming that the input is bounded or the magnitude of the input is less than or equal to a bound. Now, if this condition is satisfied, then the output is bounded. That means there exists another bounded value K2, where the K2 value is strictly less than infinity. So that the magnitude of output at any instant of time will be equal to K2, which is less than infinity. So this is the meaning of a stable system. So I have taken two examples here, one for a stable system and for an unstable system. So for a stable system, the example what is taken is the yn is equal to 100, any bounded value, 100 into x of n. So if you take x of n, the magnitude of x of n at any time as K1, then the output is 100 times K1, which is also will be bounded because our K1 is a bounded value. So the system will be stable. Now, if you, instead of 100, if I take n, which is an independent variable here, now this system will not be stable because this system equation has to be satisfied for all values of n from minus infinity to infinity. So if you take n as infinity, the output magnitude of the output will be infinity, which is not a condition of stability. So we can say that the system is unstable. So this is very simple as it looks, but as a closing remark, I want to say that most of the students have the misconception that unstable systems doesn't exist, but it is not so. There are unstable systems which exist very well. For an example, in the case of a continuous system, an integrator, or in the case of a discrete time system, an accumulator, if you see the definition, the system is unstable, because if you take an integrated and if you take integrate from minus infinity to infinity, the output value is going to be infinity. But the system exists because of the fact that we have we never in real time we never achieve the value of infinity. Thus the system exists, but by definition it is unstable. Thank you.
All right, very good. This was a very good presentation indeed. Again, we must bring to light certain very important features of the presentation that was just made and point out the merits and demerits. There are a lot of merits in the presentation that was made. In fact, one of the things you saw was that they presented both example and counter example. And one important thing which they brought out is how you develop a counter example, or rather how you prove a property and how you disprove a property. So you prove a property irrespective of example. That's very important. You cannot prove a property by citing just one particular example. That's not enough as a proof. But to disprove a property, a counter example is adequate. So this is something which we need to emphasize and we need to keep in mind as teachers. Very often students mistake themselves by trying to prove a property by virtue of example, which is not correct. So they say, well, look at this system. Give this particular input and this particular input and it gives you these particular outputs, and that is what additivity or homogeneity or shift invariance requires, and therefore the system is additive or homogeneous or shift invariant. No, that's not a proof. The proof must go beyond example. Whereas disproving a property can happen by any counter example. So this particular group brought out this point very well. You must appreciate that. One observation I had was at one point, one of you said that all causal systems are physically realizable. Now you have to be careful there. I think you meant something different, but this is what was written there, and that is not quite correct. You see, if a causal system has an infinite length impulse response, then only some of such systems are realizable. Only rational systems are realizable. So for infinite length impulse response systems, there are only some infinite length impulse response systems which are realizable, not all of them. If they are irrational, they are not realizable. In fact, that's the whole problem with ideal filters. Is that right? On the other hand, what I think was meant was that for real-time realization, causality is required. I think that's what you intended to do.
Yes,
right?
sir. Yes, sir. Yes.
So you have to be careful, when you're saying this in the class, what you're intending to say is that for real-time realization, causality is required. That's how you should frame the statement. But then later on, I think you corrected yourself by showing very good examples of non-causal systems. So, for example, you showed the example of non-real-time speech processing, which is a very good example of non-real-time and non-causal system. And similarly, you showed the example of space systems in image processing. That's also a very good example of non-causal systems which are very much realizable. Yes?
Thank you, sir.
Now, one important thing which I must appreciate here is the very nice examples of unstable systems. And Professor Prema very correctly said towards the end of the presentation that students often think that unstable systems are undesirable. They try to equate the two. That's not correct. As Professor Prema said, the integrator is a very well used system, or the accumulator, and both of them are unstable systems. Now I'm going to give you a question which I wish you to think about and answer. Think about a bank account and assume that the bank account is like a discrete system. So every month you do a credit debit to it, and let's assume that interest is calculated every month for the moment. Would you call this system stable or unstable, and why? And suppose it became stable, would you want to go and deposit your money in the bank? I want you to think about this, and we'll have some answers from you. So while we do that, I'll ask you this question again after after the next presentation. So all of you can reflect upon it. Don't let it interfere with your listening to the current presentation. But I'm going to ask you this question later on again.
Yes, sir.
So,
we will discuss.
Yes, that's right. So very good. We must appreciate. So any other critical comments on this presentation? So for the bank account, I'll give you a hint. Suppose you deposit money today and leave it in the bank, do nothing else. What would you want to happen to the money? And how does it relate to an impulse response? Okay, so this is a good hint for you. And that will tell you something about stability and instability. All right, now we'll have group 3 make a presentation. Very good morning. Yes, Prashant, is your network good today?
I don't know,
yes,
sir. You wish me best.
Yes, we wish you the very best. We wish your network all good health. We also wish you good health, of course. Yes.
Yesterday, it was a group 3 presentation. It was on, sir, I'm keeping the video off, sir, with your permission.
Yes, yes, fine. That will improve the bandwidth. In fact, I should also switch my video off so you get better bandwidth.
So this was on lecture 12 on impulse response and convolution. My group members are all listed here, sir.
Yes.
We discussed on this topic that was delivered by you, sir. And we want to discuss on the impulse response. And what is the meaning of impulse response, and such concepts are to be slowly and carefully told in the class, because this is all discussion on pedagogy. So I feel that the once the student is aware of the importance of the impulse response, he'll be able to not only do the mathematical operations carefully, also he'll be able to appreciate the role that impulse response plays in not only the time domain operations, but also in the frequency domain operations. So he'll be equipped with the capacity to analyze the systems. And for just a simple representation, X is considered input and Y is considered output. So which of this property, which of these parameters will completely represent everything about the system? Say, is it input? Does input describe the system? Because input is an independent parameter, so it has got nothing to do with the system. Similarly, the output is the response for a particular input. So is it going to define the system? So again, you can give these questions, and maybe ask them to think and maybe reply. So that will give a scope for receiving some answers from the teacher over there. So when I say everything about the system, what is that everything that we want to know? Is about some of the properties that all my fellow participants are giving. Those are very important properties like linearity, the causality, the stability, and so on and so forth. So can we characterize the system? Can we describe the input-output relation with any one parameter completely? And that happens to be, I feel, this impulse response. So this impulse response can be considered in and determined in varieties of way. That possibility we have to show in the class. Maybe we can even talk about the Fourier domain method of determining it, and the Z domain method of determining it, maybe for h of n or h of t. So just give a hint about how it can be determined, and so bring in that idea that this is a very important parameter. Once we are able to establish that, maybe at that time the student recognizes the need to describe the properties, that too especially in terms of these impulse responses. So I have one more question here, like whether I begin my discussion about the impulse responses with the h of t, or is it with the h of n? Over here h of t I'm referring to the impulse response in say time domain, and this one is in discrete time domain, continuous and discrete time. That's it. I also somewhere in your lecture that caught my attention, sir. So you were telling about the simple sequence or numbers. If they are, then it becomes easy for someone to say analyze and then quickly work out. For example, we have some number like 222, right? So if this is the case, then it is easy to work out on this number, and then we can maybe come up with the complete solution. Say the system is 3x of n plus 10. So in that case, it will be in that case it will be 16, 16, and 16, so on. Yeah. And further, I have taken as an example over here another input that is 1, 1, and 1. So if you were to combine these two inputs, the input will be 3, 3, and 3. But if you were to look at the outputs combined, it should have been 29, 29, 29 if the system were to be, say, linear. But that is not happening. So the point of telling all this thing is that if we can give these examples, simple examples, which you can quickly analyze and work out. Maybe such examples students will be able to easily analyze on their own, and then can picturize what is that about linearity, and what is that about causality, and so on. And so I say that it's easy to understand simple and smaller sequences rather than an equation like e raised to minus 2t u of t minus 1. It's quickly, it is not so much easy to picturize. Even when we talk about the convolution of the signals, it is difficult to visualize these signals, and maybe operations on them becomes further difficulty for the students, because those are the students who are just entering their maybe second year of their engineering, and especially in departments like electrical engineering, wherein we mostly talk about machines and such subjects. Introducing this signals as a just extension of mathematics will be a bit difficult. So in such a situation, I would personally feel that giving these examples, that is the discrete time smaller sequences to understand, and then build with the higher order thinking will be, I think it's a better way. And the other purpose of talking about the convolution impulse response is that we will be able to bring out the concept of this linearity also. Like input signal, if you give some simple numbers like 2 delta of n, 3 delta of n minus 1, and so on, as I have just presented it over here. Okay, so if you can represent that, break it down, and then give it to the system, because it is obeying the linearity. So if you give delta of n, it will give an output of h of n. That's what we say impulse response. So it is now 2 times delta of n. So that kind of scaled inputs and resolved and decomposed inputs, if we were to develop that idea, that will help over here as well as in the frequency domain analysis. Because next we are going to see that this these sequence of numbers can be considered as a vector, and that vector is going to be now related in terms of maybe scaled and unit in terms of unit vectors, so that naturally the sinusoidal components enter over there when we want to represent these sequences in terms of, so that that becomes the basis for Fourier domain. So that's how gradually I feel the concept of this impulse response and the convolution are to be brought into our discussion. So all the input output relations, if we want to analyze, that is what will be our final goal. So analysis of a system, then analysis of the signal for extraction of the the output. Okay. So this is what I feel. I want Dr. Gadre sir to mention these any say mistakes here, or my idea, or if there is any improvements to be done.
Yes, very good. So very nicely organized and very nicely. In fact, I'm very glad to see that one important virtue of Professor Prashant Athole's presentation is that he really exploited the pedagogy aspect here. So you see, the one very good point is that Professor Prashant Athole brought out certain pedagogical thoughts in his presentation very clearly. We must appreciate that. For example, he didn't just talk about the impulse response, he also made it clear why he should be bringing the impulse response before the student audience and what role it's supposed to be playing and how it plays that role. So you see, let me point out some good things that were said. You see, Professor Athole very correctly said, we must ask the student to reflect on what it is that characterizes the system. The input and the output cannot, because they are external to the system. But the relation between them can. And for a linear shift invariant system, how much do we need really to characterize that relationship completely? And then he quite rightly said that you could, in a linear shift invariant system, you could be breaking the input into parts and then looking at the response of each part, and that's what the impulse response does. So in a way, one experiment on a linear shift invariant system tells you everything about the system. That's the beauty of linearity and shift invariance. So in fact, this also brings out why the properties of linearity and shift invariance are attractive mathematically. Now, one point which I would like to caution you against in Professor Prashant's presentation is not to bring in subsequent ideas immediately. For example, you said you could explain the impulse response by looking at the Fourier domain or the Z domain. I would recommend that you should not mention this when you are talking about the impulse response first time, because the impulse response is something that characterizes any linear shift invariant system. But there are many linear shift invariant systems which cannot be analyzed in the Fourier domain or which cannot be analyzed in the Z domain. And then it looks to the student that unless you have a competence in Fourier analysis or Z domain analysis, you cannot understand the impulse response, which is not correct. The impulse response is the more fundamental idea, and the transform domain analysis is an idea which is developed later. This is one caution. Now, you must have seen in the way I have delivered the topic, I have emphasized that particularly to understand the impulse response, it's easier to begin with discrete time. And that's the reason why you notice that in my lectures, the discrete time and continuous time go hand in hand. Because there are places where it's easier to understand in continuous time, there are places where it's easier to understand in discrete time. So the impulse response is better understood by starting from discrete time and then moving towards continuous time. And as Professor Athole also said towards the end of his presentation, the impulse response is a culmination of linearity. You are fully making use of linearity and shift invariance when you exploit the impulse response to characterize a system. Very good. So now we'll have some more critical review, critical observations from the other participants. Would any of the other participants have any other observations or suggestions? Yes, Professor Ramchandra.
So nothing, sir, no doubt, sir. You asked one question,
Yes,
sir.
yes, I see.
Stable
In
and
fact,
unstable.
Professor Ramchandra Reddy has very correctly said the system, the bank account system should be unstable. Can you explain, Professor Ramchandra? Yes,
Yes, sir, yes, sir, with your permission, right? Can I? So suppose I had some amount in my fixed account, sir. Suppose some 100 rupees I'm speaking. So if I'm not going for any kind of withdrawal, after some time, it's going to reach to some 1 or 2 rupees or 1 or 3 rupees like that, based upon the interest.
Yes.
So regarding to the stable system, for finite amount of input, you have to get always finite amount of output, sir.
Yes, very good.
Not go beyond the applied the input, okay?
Correct, correct.
So if there is no withdrawal takes place for the corresponding amount, it's going to be the unstable. For keep on doing the withdrawal things, it's going to the stable things.
Yeah, see, stability is not characterized by your input. So your line of thinking is correct. If you put 100 rupees in your account and do nothing to it, that 100 rupees in principle will grow without bound. Otherwise, you would not put your money in that bank, isn't it?
Yes, sir. Yeah, that's going to be unstable in that case, sir.
So in fact, in that sense, the system should be unstable. A bank account system should be unstable. Otherwise, you would never put your money in that bank. If that money keeps diminishing in time, you would not put it in the bank, isn't it?
Yes, sir.
So therefore, a bank account is an example of an unstable system which you want. Very good. Yeah. Very nice. That was a very good answer.
So one more question, sir. So can you explain once again related to that stability thing, sir? If you are having integrator, all those things.
An integrator. So
sir.
You see, suppose you gave a constant input to an integrator, what would happen? The output would grow linearly.
Yes, sir.
And therefore, the output would be unbounded when the input is bounded.
Sir, is there any necessary condition you have to apply only such kind of input to the respective system to prove it is stable or unstable?
Only to prove it is stable, you must show that every bounded input gives you a bounded output.
So in most of the cases we are taking impulse, is it suggestible to take any other signals as input, sir?
No, you don't need to take an impulse every time. No. To check the stability of a system, it's not required that you should be taking an impulse every time. No. Because you know the impulse in continuous time, actually the impulse is unbounded.
Okay, sir.
Strictly speaking, isn't it? Strictly speaking, the impulse in continuous time is unbounded in that sense. Isn't it? So it's not really a good idea, though of course the impulse response tells you about the stability of linear shift invariant systems. It's not necessary that you should use the impulse as a test input, no, every time, but it could be used, right? But then, you know, in continuous time, it would not prove much. In discrete time, it would. Yes.
Thank you.
All right. Very good. Very nice. Yeah. Any other questions or any other?
There are some cases where a stable system under certain conditions will go as an unstable system. Many conditions, many real-time examples also. For example, if you take a transistor or MOSFET, as long as it is working in the safe operating area, it is a stable system. But once it goes to the secondary breakdown area, the temperature goes on increasing, and then it becomes an unstable system. So you cannot say that the system is always stable or always unstable, depending upon certain conditions also.
Yeah, see, in the language of signals and systems, if there are situations where the system exhibits instability, that means a bounded input results in a bounded output, in an unbounded output. Strictly speaking, you would call that system unstable, because there are instances where a bounded input results in an unbounded output. However, people have got around this by saying marginally stable. You know, so some people like to use this term marginally. That means in most situations, a system is stable. In most situations, a bounded input gives you a bounded output. But there are some particular peculiar inputs for which, you know, for example, if you took an oscillator, by and large, it would be stable. But then if you gave the oscillator the characteristic frequency of the oscillator as an input, then a bounded input will result in an unbounded output. So some people like to call these marginally stable. Now, of course, marginally stable still is unstable strictly, right? So even the transistor in that sense, if you look at it, if you allow breakdown, strictly speaking, it is unstable. Then you can always say that, it is a bounded input, most of the time results in a bounded output. But there are situations where, like as you said, in breakdown, it may not. Yes. Yes. Any other questions or comments?